Okay, guys. So, any questions regarding the syllabus, the course, structure, delivery mode, or any questions? Obviously, feel free to let me know right now. And like what I mentioned last time, right? There will be some videos that will be asynchronously done, but whenever the course is done synchronously, like with the class time, I will email you guys and I'll let you know if you want to attend the video lecture and also get the chance to ask questions on this material. All right, so I guess let's begin, and I'm gonna solve. So last time we worked on this problem. Today we're gonna do one last example, and then we're gonna open up a new topic in chapter 12, basically. Okay, I just want to do a very brief review, right, on what we discussed last time. We said the acceleration, right, is the rate of change of the velocity with respect to time, right? And the velocity is the rate of change of displacement with respect to time. Okay, so if you actually take dt and then dt from here, you can make another equation, which is a ds is equal to vdv, right? And in reality, what really happens is that this is only like a very small change in position and then a very small change in the velocity, and that is how they are related. If you want to get the overall, the difference in the velocities, basically, or the position, you would have to integrate that, and then when you integrate this relationship, you have to have the same lower boundary. So here you have an acceleration that is applied on an interval from s0 to s1. The velocity will actually go from also v0 to v1, right? And because here you have vdv, you can integrate this guy, and it's going to be like v squared over 2. Again, your boundaries are v0 and v1, and you could also write that as 1 over 2 v1 squared minus v0 squared. All right, it's pretty basic. So let us actually do example 3. And we'll go from there. So in example 3, we have a particle that is moving along a straight line such that its acceleration is defined as a is equal to minus 2v, where v is in meters per second. If velocity is 20 meters per second, when time is equal to 0 and s is equal to 0, we need to find the particle's position, velocity, and acceleration as a function of time. Okay, so let us write what is actually what we have. And so here we know the acceleration is equal to minus 2v, right? How can I get, for example, acceleration as a function of time? Can anyone take a guess on this? Any ideas? Okay, so here basically they gave you the acceleration as a function of the velocity, right? So if your velocity is 0, your acceleration is 0, right? I'm sorry?
دكتور مش في رول للفي بتقول انه هي في equal AT plus V0 مستعمله شيء ولا لا؟
V is equal to AT plus V0. Can someone comment on this? Is that true or not true? Well, this would only be true if the acceleration is constant, right? If the acceleration is constant, and then you're taking the integral then. But here the acceleration is actually not a function, not a constant, right? It's a function of the velocity.
Yes,
right?
yes.
So I think the best way of doing this is basically by separating that, right? And we well know that what is acceleration? Acceleration is actually equal to what? dv over dt, right? So dv over dt is actually equal to minus 2v, right? So, can we simplify this more? I think this is like a separable, right, differential equation. I can actually bring v over here, so I can actually rewrite that as dv over v is equal to minus 2 dt, right? Okay, so if I integrate this guy and I integrate this guy from time 0 to time v, and then this guy is v0 to v, right? What happens now? Can I?
هتصير لن في
Exactly, ln, right? So this is ln of v over v0 is equal to minus 2t, right? So remember, when you have an exponential here, it's t minus 0, basically, right? So this is t minus 0, but obviously 0 is 0, so it will be minus 2t, right? Okay, so now we are close, but yet we don't have the velocity as a function of time, right? I mean, we have it, right? But it's like more indirect way or informal way. Can I simplify this further?
Yes, doctor.
How?
نعمل exponential both sides.
Exactly, we do the exponential, so I can do e. So basically, if you do e to the exponential of log v over v0, it will be v over v0 is equal to e minus 2t, right? So now we're good, right? Now we have the relationship. So now I can say that v is equal to v0 e minus 2t, right? And from our example, what is velocity initial is 20, right? So your velocity is equal to 20 e minus 2t, okay? So now if we were to get the acceleration as a function of time, how can I get the acceleration as a function of time?
كان عندنا الفورمولا A equal minus 2v يعني A equal minus 40e minus 2t.
Exactly, so A is equal to dv over dt, which is equal to minus 40 e minus 2t, right? So this is your acceleration. And then how about the position?
نعمل integrate مرتين.
Exactly, you can integrate this guy twice or you can integrate this, right?
Yes.
Okay, does anyone know what is the integration of this? And then this guy is 0 to 3.
20 over minus 2 e minus 2t.
Bravo, 20 over minus 2, right? E minus 2t, which is equal to minus 10 a minus 2t. Okay, and that's it, guys. We are done with these examples. Okay, great. So let's continue with our lecture. So now we're gonna look into, sometimes you actually have the velocity as a function of position or the acceleration as a function of time.
بس عندي سؤال قبل عن هيدي. بس عملنا انتجرال من 0 ل t مش بدي احط مرة t مرة 0
Yes. You're actually
بس احط 0 رح يرجع.
You're actually right. So here we have 0t, right? And then the 0 actually doesn't disappear, right? Because e to the power 0 is actually 1. Very good. Yes, very good observation, actually. So, right. So when you are integrating the exponential, you still have to have the 0, right? And e to the power 0 is actually 1, right? Or any number to the power 0 is actually 1. So minus 10 e minus 2t, right? So this guy is t and then 0, right? Which is equal to minus 10 e minus 2t, right? Minus 1, right? So if you multiply this by minus, so it's going to be 10, 1 minus e minus 2t, right? So so we want to make sure you want to evaluate that properly, right? Okay, very good. So let's continue with our discussion on this. So sometimes actually you have the velocity is given to you as a graph, right? The velocity as a function of the position. And sometimes you actually have the acceleration as a function of time or the velocity as a function of time. Let's say later on you ended up working in, as a, hardware test engineer or development engineer or whatever, right? Sometimes you actually have your acceleration as a function of time because you could have a sensor, right? An accelerometer measures the acceleration. So if you have an accelerometer that gives you acceleration as a function of time, you can technically use that signal to be able to find out where the object is, right? By integrating the acceleration as a function of time, right? And then you will have the velocity as a function of time. If you integrate this one more time, you get the position as a function of time, right? So this is how you can. So many times, basically, your velocity or position, etc., is given to you as a chart or as a graph. And let's look into how we can use a chart to be able to identify where an object is. All right, so I'm gonna begin by looking at ST graphs, or position as a function of the time graph, right? So if you have, if the position is given to you as a function of time, right? How can you get the velocity, let's say at time t1? Well, we know the velocity is equal to ds over dt, which is essentially the slope. So simply by getting the slope at that particular point, you actually get the velocity, right? And then likewise, time t2, basically, the derivative will actually is essentially the slope. So simply getting the slope of the position curve as a function of time, you can actually get the velocity, right? And then likewise, if you have the velocity as a function of time, can someone tell me, like, how can I get the acceleration at time? What would be the acceleration at this time, basically, where the curve basically meets the horizontal line? Can someone tells me? What
is
is
the
that?
area under the graph.
Right. Someone else has a suggestion?
I mean, using
Can you repeat the
integration.
question?
Yeah, so the question is, what is the acceleration of this particle at this instant, basically, where the velocity curve meet the horizontal time axis?
زيرو، مش إنه ما في no change.
Right, well, how is
It's
acceleration?
maximum.
Isn't it perpendicular to the velocity line?
No, well, let's see. Well, let's look at it. So A is equal to dv over dt, right? So A is basically the slope of the velocity curve. So if I give you the velocity curve, right, then the acceleration here is not zero. The acceleration actually is a slope, right? And do you think the acceleration here is negative or positive?
Negative, of course.
Negative.
لأنه V is
Negative,
decreasing.
right? Yeah. If you look at here, right, so dt is always positive, right? When you are differentiating an object, you always assume you're moving in a positive time change. So whatever dv happens to dv, right? So if you are moving from left to right, because time is moving from left to right, what happens to dv? dv is basically decreasing here, right? If you take, like, a tiny element here, for example, you will see that dv is actually decreasing. Or if you actually look from left to right, if the slope is going down, that means that it's a negative, right? And if it's going up, then it's positive. So in that case, the acceleration is going to be negative, okay? How about the velocity at the top here? What would be the velocity? Can someone take a guess?
Zero.
Zero,
The
yeah.
velocity is zero. Why? Because exactly you have a zero slope, right? So the slope is horizontal, meaning that your velocity would basically be zero. If the velocity is zero, do you think the acceleration would be zero?
Yes. لا مش ضروري.
Exactly. It's not necessarily, right? It's not necessarily. Okay, let's continue and then look into more of these guys in detail, right? Okay, so let's look into this right now, okay? Let's say that you have a sensor, right? You're working on, you're on a robot, for example, or, any object that is kind of moving, right? And then you get the acceleration as a function of time. Okay, let's say this is your acceleration as a function of time. Okay. I want to ask you guys, what happens if I want to find the velocity at time t1? Okay, let's say here you have t0, right? And then this is time t1. And basically I have a sensor that has given me that signal, right? And then obviously here, let's say it's in meter per second squared. Okay, can I find the velocity at time t1? How can I find the velocity at time t1?
We have to integrate
Great.
the equation.
Exactly, so we would have to integrate, exactly. So the velocity, right? We're going to integrate the acceleration dt, right? But what are the boundaries? Here, obviously, is a variable, right? So what should be the boundaries on the integration?
مش T0
T1.
T0 and then T1, okay? Okay, so essentially, when you do so, basically, you are simply finding that shaded area, right? Okay? And then is that it, or do we have to add more stuff to it?
Yes, plus V0. In case
Plus-
it wasn't zero.
Plus, not V0, basic plus V at time T0, right? Basically, you should think about it that way, right? When you are integrating, basically, this will give you, right, the contribution of the acceleration. So if you have applied some acceleration between time t0 and time t1, this will be basically a change in velocity. So the area under the curve is basically a change in velocity from the velocity at that point. If the velocity at t0 is 0, then obviously that would be it. Okay. Let me actually give you one more example on that. Let's say if I want to actually find, so let's say I have here like T2 and then I have T3. Okay, can someone tell me what physically this area mean? Okay, what is the shaded area here basically? Can someone tell me what would that mean?
It's the velocity between T2 and T3.
The velocity?
The change
the
in
average
velocity.
velocity.
Change of velocity.
Exactly. So this is a change in the velocity, right? So here you can think of it, let's say you're driving a car, for example, right? And then this is your acceleration profile. So this area, right, it will actually tell you how much change you had in the velocity, right? Can you actually tell the absolute velocity of your car, for example, based on this curve?
No, based on this area only.
Yes, based on this area. Can you tell your absolute velocity?
No, shouldn't we take the whole curve?
Exactly. If you want to take the whole curve, then you're going to consider the velocity at time t0, right? If you actually only consider this area, basically this will tell you the change in the velocity, right, from the velocity at time t2. So whatever that velocity had at time t2, you're going to add this shaded area to actually get the velocity at time t3, right? So think of it as simply basically a change in the velocity, right? So this shaded area, right? So if I actually, it will actually give me the velocity at time t3, right? So this area, right, which basically is integrating this guy from T2 to T3, right? Plus, I'm gonna actually add to have the velocity at time T2, right? Because this is what it is, right? So, dv is actually equal to ADT, right? And then when you're integrating this guy from time T2 to T3, right? This guy is what? Like, V2 and then V3, right? So you wanna make sure about the boundaries of how this basically operator works. Does it make sense? Okay, the same thing basically applies for the position, right? If I actually gave you, let me draw this. Let me say that I gave you the velocity as a function of time, right? And this time I'm actually gonna make it look like this. Okay, and then let's say this is T0, all right? Can someone tell me again, like what is that shaded area here from T0 to T1?
It's the integral.
Distance traveled between T0
Exactly,
and
so
T1.
this is a distance traveled, right? It is a distance traveled from time 0, right? So basically S at time t1 is basically equal to the integration of the velocity from t0 to t1 plus position at time t0, right? Okay, you will basically always add that initial position, right, of your lower boundary. Okay. If you were to look into this whole thing, right, let's say this is TF, and then you basically, if you integrate those two areas and the whole thing is basically 0, what would that mean? Basically, it means that you your position, you have went somewhere and then you came back to 0, right? Basically by integrating all this area. All right, so what I want you guys to know here is that when you are integrating the area, it's only relative to the first point that you are using, right? If I integrated this guy, let's say this guy is T2 here, right? If I integrated this guy, if I found the area under the curve between T1 and T2, and here the area would be negative, right? If you do this guy, right? Basically, you're finding the position at time T2 starting from position at time T1, right? So S T2 is equal to S of T1, right? Plus V dt T1 to T2. Okay, so just remember that, right? So if you have, this is your boundary here is, you're starting from T1, basically, you're gonna integrate this guy from T1. Okay, because this is not absolute, right? To make it absolute, you have to add basically whatever position you initially had. In other words, basically the when you do that integrand basically, right, it will simply tell you the change. If you're integrating the velocity as a function of time, it will give you how much basically the difference in the position, right? Simply difference in the position, but you need to know where you initially were before that velocity was applied, right? If the velocity applied is 0, right, you had the initial position basically, right? If the velocity is always a straight line, then your position will be where you initially were, right? And any action that you do basically, you begin to basically build it up, right? You build your position as a function of time basically, right? This is really what is actually happening.
دكتور
Yes.
ما فهمت اس اوف تي 1 ليه ما حطيناها انتجرال اوف في من تي 1 للبوينت 0 هاي الانترسكشن.
I'm sorry, what is it?
ما فهمت ليش اس اوف تي 1 ما عملناها انتجرال from t1 to the intersection of the curve of v by the x-axis.
Okay, so s of t1, which is here, right? Okay, so you're finding
okay.
the position at time t1, and you basically have the velocity as a function of time. You're integrating the velocity, right, from t0 to t1, plus I'm using st0, my initial position at time t0, whatever it is. You have to basically add it to be able to actually get your actual position.
طب يعني اس اوف تي 2 هي كيف كانت؟ يعني اس اوف تي 2 المفروض تكون انتجرال من تي 1 من تي 1 لتي 2.
Okay, and that's what we did, right?
ليش حطينا اس اوف تي 1؟ اوكي لانه الانيشال اوكي فهمت اوكي.
Okay, so s of t1 is always your initial position, right?
Yes, okay.
S of t1 basically will be your initial position where you are basically starting to add that velocity. Okay, we'll have a few examples,
okay.
and you will be able to really understand that in a bit more detail. But that is the idea, right? If you have an acceleration as a function of time, right? The area below the curve, basically, whatever that you do, basically, it's like, you know, when you have an acceleration applied, basically, right? This will, when you integrate the area below this acceleration curve, it will simply tell you the change in the velocity. Okay, if you are integrating, you are simply getting the change in the velocity. But when you go backward and then get the slope, like in the case of the velocity, if I want to actually get the acceleration at this time, it's simply the slope, right? It's an absolute value, right? Here, the acceleration at that instant is whatever it is, right? So simply the slope of that curve. But if you actually have the acceleration as a function of time, right, and then you're trying to get the position, any integration that you do, you always have to look at the initial boundary where you are starting that integration, and then you have to add basically what was the velocity at that time. Okay, and obviously this is, you can also understand it in another way, right? Let's say you have an object, you know, flying in space, right? The object will continue to fly with the same velocity, right? If there are no forces applied on it. So the velocity will not change unless you actually have acceleration, or unless you actually have some external forces resulting in acceleration. So if you have an object flying in space, it will have the same velocity, right? Now, let's say you want to accelerate that object, or you want to decelerate it, basically, it will basically respond to the acceleration. So we will always have the velocity is equal to your whatever current velocity plus the integration of the acceleration times dt, starting from the value that the acceleration is being applied. Okay, I think that should be it for that. And so here's what we have in our notes, basically, right? So when you are integrating, basically, you're getting that delta v, right? And you will always need to actually add the initial velocity to be able to get the absolute velocity. Same thing for a VT curve, basically, right? When you are integrating the area under the velocity, it will simply give you the change or the difference in the distance, right? Or the change in the distance. To get your absolute position where you currently are, you have to basically add that DSTT. Maybe I can even try to illustrate that even more. Let's say you actually have, like, you know, this is your S axis, right? And you have an object that was initially like at this value as 0, right? And now this object basically is beginning to have some velocity. If I want to find its position at time S1, basically, right? So S1 is going to be equal to S0 plus VDT, right? From to 0 to T1, where T0 is here and then T1 is here. All right, so you always basically add your initial position where the velocity is being applied on an object. Okay, last thing that I want to go over here is basically sometimes you could actually have the acceleration as a function of the displacement, so AS curve or VS curve basically. All right, and we remember this equation, or how we basically obtain that equation, right? By substituting t basically. If you have basically the acceleration, let's say I gave you the acceleration as a function of position, right? So let's say you have an accelerometer, and then you also have a way to be able to measure the position directly, right? So what do you think that curve is going to be? Like if I took some, this is distance S1, and then this is distance S2, right? So this is ADS. Can someone tell me what is that equivalent to? Right, what is the integration of ADS? Remember, it was VdV, right? VdV from
VdV,
V1 to
yeah.
V2, right? Which is V square over 2 V1 V2, right? Which is 1 over 2 V2 square minus V1 square. That's good. So basically, if I'm actually integrating this area, can I find the velocity at position 2? Can someone tell me if I can do so or not? How can I find the velocity at that position? It's okay, guys. You can take a guess. No need to know it.
We plug in the equation يعني مثلا a number and it gives us the velocity at this position.
Yeah. Okay, Jahan, say it one more time.
مش like for example if you want to find the velocity at position S2 we plug in مثلا number S2 in the equation بيطلع لنا velocity.
بطلع لك velocity, right? But let's say I give it to you graphically. Let's say A is given to you like graphically, right? And you are basically able to. You need V1, مظبوط?
V1, the velocity at S1.
Exactly. So you need V1, which is the velocity at S1. Bravo, exactly, right? And then we're going to be able to find V2. If I changed S1 to S0, then you would need what?
V0.
You need V0. Okay, it's pretty basic, guys. It's really, really simple. So let's do that. So basically, we're going to multiply this area by 2, and then we're going to find V2. So V2 squared is going to be equal to 2 times ADS, S1 to S2, plus V1 square, right? Remember here, basically, you are obtaining, all these are basically squared, right? So if I change S1 to S0, then V1 is going to be what?
V0.
V0. You can change it to any value, and then it will also be like that. Okay? There's one more thing that we can actually get from these curves. Let's say you actually have a V versus S curve, right? If you have a V versus S curve, that is something that you can actually get out of it. And then here I'm showing you to this. Basically, we know that ADS is equal to VdV, right? So I can actually write A to be equal to V times dV over ds. Okay? So dV over ds is equal to what? Is the slope of the VS curve. So if I actually have the velocity as a function of the position curve, I can get what? I can get the acceleration at any point. So let's say you're trying to get the acceleration at that point. How do you get the acceleration at this point? Can someone tell me? You multiply the current value of the velocity, right? So let's say you want to get the acceleration at, s is equal to like 2 meters, right? So you go to 2 meters, right? You go up, you find what is the velocity, because you already have the velocity as a function of s, right? You find the velocity, and then you multiply the velocity by the slope, which is dv ds, also at the same position, right? So you simply multiply v times dv over ds, and you'll be able to get the velocity. Okay? Okay, the best way to learn is by doing examples, right? And practicing on doing the assignments. Obviously, here you will kind of get like, kind of like an image of what actually is supposed to happen, but there's nothing like actually doing examples and then solving the assignments. So let's actually start by doing example 4 in this lecture note. So if I tell you that the velocity of a car is given to you like that, basically from 0 to 40 seconds, your velocity is 10 meters per second. And between 40 to 80, the velocity begin to kind of decrease, right? Although in reality, this is never possible, right? Okay, yeah, obviously at some time t0, you could actually have a velocity. So you started the clock when the car was already moving, okay? How can I actually find the total distance that the car has traveled?
We do the area under the graph.
Bravo, yes, exactly. So I know that what V is equal to, how is the velocity and position related? I know V is equal to ds dt, right? So I know ds is equal to V times dt, right? So I can integrate this guy from 0 to total S, and then this guy from 0 to final, right? But here the velocity basically is built out of two functions. So the total area, which is S, total distance, I'm sorry, is equal to 0 to, let's say, 40, مظبوط, V1 times dt, where I have to basically express V1 as a function of time, plus V2 dt, integrating this guy from 40 to 80, right? Because V1 and V2 are two different mathematical functions. But if I don't want to actually get into the details of obtaining the equations of the line, then putting the velocity as a function of time, I can basically just look at the area, because I know this guy is equivalent to the area of the first equation, right? Or under the first line. What would be the area if I want to just use geometry? Can someone tell me?
10 times 40.
Exactly, 10 times 40, right? And then that is
That's,
meters. How about this one?
10 times 40 over 2.
Exactly, or 80 minus 40 over 2, which is the base, times the height, which is 10. And that's it, right? So your actual distance that you traveled is area under the curve, which is 10 times 40, plus 40 over 2, which is 20 times 10, which is so 400, plus 200, which is 600 meters. Okay? Very simple, guys. If I want to actually express that as a function of time, what would be V1? Can someone tell me what is the equation of V1?
10.
Exactly, bravo, 10. Right. How would you get the equation of V2? I'm not going to ask you that, because I mean, you can get the slope, for example, right? And then you can get the equation of a line, right? If you were to construct the AT graph, how would the AT graph look like for this car?
0, then decreasing.
Exactly, right? So initially is what? Y is 0, because the derivative of a horizontal line is 0, right? So the car had no acceleration. How about here? It's going to be like that, right? You guys agree?
Doctor, why isn't it a curve?
مش لازم تكون like a curved.
How should the acceleration be like between 40 to 80?
And if the velocity is a straight line, the acceleration should be a curve.
Should be what?
Because it's a curve, مش straight line.
Curve. Why is it a curve? What is that? Is it a parabola?
مش constant بتكون دكتور؟
Constant, yes, constant. I'm looking at acceleration, not the position, right? Okay, okay, what should I draw here? Like, you know, I'm on an exam right now and I want to try to write this. What should I write? How does acceleration look like?
لما بجيب الايكويشن تبع الستريت لاين تبع الفي وبعمله ديريفاتيف بيطلع معي ايكويشن تبع A in terms of T بقدر ارسم الكيرف.
You can, yes. Or there is also definitely a viable solution. The other way would be to simply look at the slope, right? How do you find what is the slope of this line? It's, by the way, a constant, Maike. Is it positive or negative?
Negative.
Why?
Because it's decreasing.
Because exactly from left to right, the line is going down, right? From left to right, the line is going down. So what would be here? The slope is dy over dx, right? What is dy? 10. No, dy.
10. Sorry, 10.
Right? A is actually equal to dv over dt, right? So what is dv in this case? dv is minus 10, مظبوط. What is dt? 80 minus 40, right? Which is 40, مظبوط. So minus 1 over 4. So minus 1 over 4. So basically your slope is what? Is a constant line, مظبوط? That is negative, right? Minus 1/4 meter per second square. Okay, guys. So this is your acceleration. So the acceleration is like that, and then it has like a jump into it, and then it goes like that. Okay. In reality, later on you'll learn in your mechanisms course something about jerk. Has anyone heard about jerk in mechanisms? Jerk. Okay, jerk is
vibrations, doctor.
مظبوط. Jerk is the derivative of dA dt, right? So you don't see that in motion in what we're doing, but jerk is the derivative of the acceleration. So in machines, for example, for the machine to have a very smooth operation, the jerk would have to be continuous, right? Only if you do the jerk, what would be the jerk here? It would be infinite, مظبوط. Over a dt, basically you are jumping infinite. You're jumping from here to here, basically. So the slope here is infinite, مظبوط. So okay, so later on you'll actually see that. I think we have 2 minutes left, so I'm gonna actually close this meeting and I'm gonna log it back again. All right, so just join back in.